Welcome to my talk. It's a pleasure to meet you here. I'm Endo. I would like to thank the organizers for the opportunity to present here. Today we are going to talk about metastate on 1D long-range Z model with random boundary condition. We will introduce the random Gibbs measure, the metastates, giving some classical results and our result on the 1D long-range Z model. This is a jointly work with Arnold van Enter and Arnaud Leny. Let us introduce the Z model. Let lambda be a finite subset on ZD, omega lambda be the set of spin configuration in lambda, sigma an element of omega lambda, and eta, a configuration outside omega lambda, is called boundary condition. The Hamiltonian of the easy model is given as the following, where J are the interaction and H are the external fields. We say that the easy model is ferromagnetic if the interaction is non-negative. It is nearest neighbors if the contribution of the interactions is only on the nearest neighbors of the lattice, and long range if the interaction decays polynomially. In this talk, we are going to work on the longer range when d equals 1. If you are interested to see results related to the other d's, check Lucas Afonso's talk, who will talk about phase transition and light deviation in the long range Z model. Now we are introducing the random Hamiltonian, which is a random variable on a certain probability space, where we randomize some parameter of the Hamiltonian. For example, the random field is the model where the external field is IID symmetric random variables. The Edward Anderson spin glasses is when we randomize the interaction, where the distribution could be, for instance, the centered Gaussian or symmetric -1 and 1. We can also have the random boundary condition, where each spin of the boundary has symmetric distribution on -1 and 1. We are interested in the third item. Random Gibbs specification are probability measures with the law given by the exponential of the negative inverse temperature times Hamiltonian. Z is the partition function. Note that the random Gibbs specification are random variables on the probability space W. Now, we define the random Gibbs measure as the probability measures measurable on W, satisfying almost surely what we call the d-hour equation. It is natural to ask whether the Gibbs measure exists, since compared to the ordered system, they have to be random variables on W. In order to analyze the existence of the random Gibbs measure, let us work on the weak limits of a sequence of random Gibbs specification. We can try among three ways. Let us analyze each one. The first one is the convergence almost surely along random subsequence. We know, by the compactness of the set of Gibbs measure, that for a fixed omega, there exists a convergent subsequence of the random Gibbs specification. The main problem here is whether the limit is measurable. Since the set lambda depends on omega, it is hard to control them in order to show the measurability of the limit. So, let us consider this option. The second one is the convergence almost surely. Here, lambda doesn't depend on omega. A good news is, this convergence is typically the same as the ordered system. This means that almost surely, the sequence has the same behavior as without randomness. On the other hand, by the same reason, this is a bad news. As Newman and Stein pointed out, this is unlikely to happen. We are asking a too strong convergence. Then, it only remains to us the third option, the convergence in distribution. By compactness, the distribution converts for non-random subsequence. So, we don't need to worry as in the item 1. And even that the convergence in distribution is weaker than the convergence almost surely, it still keeps the information that we want. So, it seems a promising convergence. Let us analyze a bit more about this convergence. But before, if you are interested in more details about this analysis of the convergence, check Bovier's book. I also suggest checking Bovier and Gaillard's paper. To understand the convergence in distribution, let me give you an example on the ferromagnetic nearest neighbors easy model. In the ordered system, we know that there exist two extremal Gibbs measure, mu plus and mu minus, such that mu plus is a weak limit of the sequence of Gibbs specification with plus boundary condition, and the same as mu minus with minus boundary condition. They are distinct at low temperatures and equal at high temperatures, meaning that the model undergoes to a phase transition. Moreover, At t equals 1, they are equal for all temperatures, so there is no phase transition. In the disordered system, for a fixed omega, the sequence of the Gibbs specification may have two different limits for two different subsequences of lambda. For example, it can happen that one converges to mu plus and the other to mu minus. This is not special in the disordered system. Even in the ordered system, it could happen for a suitable boundary condition. The main problem is how to control the possible limiting measure given omega. To solve it, we use the convergence distribution, and now we are prepared to define the metastates. Metastates are measurable maps on the probability measures such that the set of the Gibbs measure obtain full mass. The metastates describe the weight distribution over the possible limits Gibbs specifications. There are two ways to construct metastates: the Eisenman-Weyl metastates and the Newman-Stein metastates. Newman showed that both constructions return the same metastates. Here, we focus on the construction of the Newman-Stein metastates. Newman-Stein wrote many papers about metastates and the metastate formalism. They define the random empirical metastates, as we saw in the analysis of the convergence. They show that the sequence, in fact, convergence distribution, but only when the sequence of lambda is sufficiently sparse and on subsequence of this lambda. The assumption, at first, looks technical. However, Kusko shows that in the Kuhn-Weiss random field Ising model, we can't remove the sparseness. Here, I list some of the several papers related to metastates, such as spin glasses, mean fields, random boundary conditions, and some others, like random fields, Hopfield models, and for general models. Check the reference for more details. 1D long-range Ising model is a ferromagnetic model where the interaction decays polynomially with power between 1 and 2. Dyson showed the phase transition when alpha is between 1 and 2, and Froelich and Spencer showed for alpha equals 2. There are only two extremal Gibbs measures, mu plus and mu minus, and all the Gibbs measures are translation invariants. We are going to consider the random boundary condition as the disordered system. To find the metastates, we need to analyze the energy of the boundary, as given by W. Using the symmetry of the distribution and the translation invariant, we can work with the boundaries on the negative side. We know that any Gibbs specification is approximately equal to the convex combination of mu plus and mu minus, where the weight is given by small lambda. To find the metastates, we have to find the distribution of this weight. Here is our main result. We show that, at sufficiently low temperature, if the decay of the interaction is low enough, then half of the volumes the Gibbs specifications are close to the plus Gibbs measure, while the other half are close to the minus Gibbs measure. If the decay is fast enough, then the metastate is supported on the whole set of the Gibbs measures. The value of 3/2 comes from the analysis of the random boundary energy. For each positive side I, the random boundary energy on I has expectation 0 and standard deviation the size of I to the power half minus alpha. An interval of size n scales like n to the power 3/2 minus alpha. You obtain the result by a local limit type argument. Here we list some references. Thank you very much for watching my talks. Enjoy the other talks and the symposium.